Sushruta for NEET is now available on the Google Play Store. Try it out for free.
Hi students, so we continue with our discussion of LC circuits. So this is the class 12 continuation. So as we indicated, the angle, phi angle is obtained by taking the tan inverse of the the impedance, which is the difference between the X and the C, XC and XL, right? So you take XC minus XL divided by R. The imaginary component is XC minus XL. The real component is R. So XC minus XL by R, and take the tan inverse of that. That will give you the phase, right? Now, we also looked at the analytical solution, and then we looked at how impedance theory, turns these equations into. Was she able to join? Excellent. Welcome. Wonderful. Happy Navratri. So let me continue. So today we are continuing discussion of the LCR circuit, and so in LCR, what one does is one takes the impedance and divides it by the resistance, and that gives you the phase angle, the tan of the phase angle. Tan phi equals XC minus XL by R, right? So now the next idea is this idea called resonance. Okay, there is a point when there is not a point, I will say there is a frequency, what is called the resonant frequency, at which the L and the C completely cancel each other out in this LC circuit, RLC circuit. And when they cancel out, you end up with the RMS current being Vm by R, because the second term goes to 0. So the point where the second term goes to 0, XC equals XL, is where omega L equals 1 over omega C. Okay, so omega L equals 1 over omega C, which means that omega square equals 1 over LC. And when omega square equals 1 over LC, you have omega equal to square root of 1 over LC. So at that point, you have resonance, and that is the peak point here. That is the point when there is most energy transferred from the source, the voltage source, onto the resistor. Okay, so now if you look at the power across the resistor, it will follow this kind of a band pass kind of frequency response. So the I versus the omega will follow this kind of a curve. Now the things that we are going to discuss deal with the width of the L and C. They determine the actual omega, but how thick is it, right? How thick is the band, right? So, and that is called the bandwidth. Okay, so W1 minus W2 equals 2 delta W. If you see the red lines, that is W2, this is W1, and the distance between the two is 2 delta W, and that is called the bandwidth. And the bandwidth is essentially, so you have omega naught and one delta omega this side, omega naught, another omega, another delta omega that side, and that gives you the bandwidth. Now, the delta is, so if you look at it, the delta omega, right? So that is R by 2L. Okay, and when you look at the delta omega and you call it R by 2L, then you also measure this other term called the quality factor. So now this is the delta omega sets 2 times that will give you the bandwidth, right? And the So R by 2L is delta omega, and now then you have the sharpness is measured using what is called the quality factor. So how sharp is this, right? So is it like that or is it like that? Okay. So now the sharpness or the quality factor is omega naught, which is the frequency there, divided by the bandwidth. So omega naught divided by the bandwidth will give you Q. Okay. And so so it is omega naught L by R. Okay, because delta omega is R by 2L, so omega naught by 2W, the 2's will cancel, therefore you will have omega naught L by R. That will give you the quality factor. So using, if they give you an RLC circuit and ask you what would be the quality factor, you first get the omega naught, 1 by root LC. Once you got the omega naught, then you do omega naught L by R to get you the quality factor. Okay. So, so those are simple types of questions. I am sure you can understand what I am trying to say. And then if you don't, feel free to ask me. Okay. Now, here's a simple example. That's why they have these simple examples. The current lags by the same amount by the current leading. On taking, so here's the question. In a series LCR circuit, R is 200 ohms, and the voltage and frequency 220 and 50 hertz. On taking out the capacitance of the circuit, the current lags behind the voltage by 30 degrees. So that is your tan phi. So tan 30 is what? 1 by root 3. So tan 30, so it's 30 degrees means 1 by root 3 is what? Tan 30 is 1 by root 3 equals R by omega L. Okay. So R by omega L. So from that you can calculate the L. On taking the inductor from the circuit, the current leads the circuit by 30 degrees. So what they are saying is that so that is 1 by omega C, right? So now, what is the power dissipated in the circuit? It is omega square by V square by R, because if this is 30, that is minus 30, then they will cancel out. Okay, so this phase angle is plus 30, that phase angle is minus 30, then that means that when you put both of them together in the RLC, they will cancel out. The circuit is in resonance. So as a result, your average power will be V square by R. Okay, what happens is, in such situations, in one circle, in one part of the circuit, as this one is charging, the other one is discharging. That is, when the capacitor is charging, the inductor is discharging. When the inductor is charging, the capacitor is discharging. So they cancel each other out, and therefore the average power will be V square by R. Okay. So now, so these are pretty much the the same set of equations, resonance, etc. And you can build, you can find, so when you have max power, you have max power when there is resonance. And when is there resonance? When omega naught equals 1 over square root of LC, right? Therefore, at that point, what is what is the corresponding power? You can find the corresponding power, and you can see that the power, the current is maximum there, right? So maximum power comes when you have maximum current. Okay. Therefore, from that you get I square Z. Okay. So now let us go to the next factor. Delta omega equals R by 2L, right? And quality factor equals omega naught by 2 delta omega. 2 delta omega is what? 2 is the bandwidth. So quality factor is the resonance frequency divided by the bandwidth. Okay. And therefore, using these, you can then do a lot of calculations. For problems come, you should be able to answer all of them. Okay. This, these are the kinds of things that they will try to quiz you on in a NEET exam. NEET exam is not an exam like the JEE exam where they ask you very, very tricky stuff there, but they want to know if you've understood all the concepts. Okay. So now let's look at this. Okay. So now an RL circuit, right? In a pure RL circuit, the voltage, if you just have R and L, the voltage across the R will reflect that of a low pass filter. The voltage across the L, on the other hand, will reflect that of a high pass filter. Okay, and so what is the corresponding voltage? You can calculate that V out. If it was a DC supply, the inductor will be a short, right? So what does that mean? The voltage is zero if it is a DC supply, right? If it is an AC supply, the higher the voltage, the higher the frequency, the higher the voltage across the L, right? Because it is V equals IR, like that. Here V equals omega L times I, and so as a result, the higher the omega, the higher the I omega L. Okay, it's that simple as that. Okay, so remember that part. In a DC circuit, a capacitor will behave like an open. It will act as though there is no. If you just attach a capacitor to a battery, right? It will just charge the capacitor, and then eventually, steady state, there will be no current. Okay. Now the inductor is the exact opposite. Steady state, the inductor will act like a short. Okay, like a short circuit. You will have almost like there is no resistance. In the case if you connect it to a DC voltage. Now here, what are we doing? We always connect it to an AC voltage. So AC voltage means it will have higher and higher. If you keep increasing the omega, correspondingly the voltage across the V out in this figure will increase with the increase in omega. Okay. Now, and the voltage across the R will correspondingly be higher when the omega is lower. That's why we say the voltage across R will be a low pass filter, and the voltage across L will be a high pass. So the voltage will switch accordingly. So you must remember that, and it is opposite when you have an RC. Okay, so here you have VIN divided by R square plus omega square L square. So this is R square is your real part, omega square L square is your imaginary part. So you have the real and the imaginary. The real is R, the imaginary is omega L, and therefore you square root of A square plus B square will give you the third side of the triangle. That will give you the effective magnitude of the impedance. Okay, VIN divided by square root of R square plus omega square L square. And therefore from that, so now the voltage across L will be this multiplied by L omega. Okay, as omega increases, V out increases. That's what they are saying here. Now in this case, larger the omega, lower the V out. So that is the two examples which reflect the low pass and the high pass in a LR circuit. Okay, that's what they are saying, with these two figures. Okay, so so there is a certain continuum here. Now, what happens to power? Okay, so power in a in this kind of a AC circuit, right? The power is highest when XL equals XC. Now, what happens when XL equals XC? The tan of the angle also goes to phi, also goes to 0, and when phi goes to 0, you have the peak power. Okay, so maximum power is absorbed at that point. So the voltage across the resistor in a series RLC is a band pass. Okay, so it will be highest when you are in that band, and that band will be on either side of omega naught. Okay, so that's why we say band pass. You can see this is a standard band pass. Power versus omega, right? So what is omega? Omega is the frequency, right? So for a band of frequencies around omega naught, you will have maximum power. Okay, now for if there was no resistor, then you will have a wattless circuit. So then in that case there is no power that is dissipated. Only a resistor will dissipate power. The capacitor and the inductor, they will just transfer power to the battery and then give it back to the power source. So that's how in the case of an AC. Okay, so the maximum power is V square RMS by R. Maximum average power is maximum when you have XL equals XC, and the maximum power is V square RMS by R. Okay, and so now how do we calculate this omega and Q, right? What is Q? Q is omega naught by bandwidth, right? So now what is omega 1? Omega 1 is R by 2L, right? R by 2L is called alpha plus or minus root of the impedance, right? So now omega 1 minus omega 2, that omega R by 2L is delta omega, right? R by 2L is what? Is delta omega. So omega naught by 2 delta omega, you will end up with omega naught L by R, which is the quality factor, right? So that is an indicator of how sharp that band pass is. Okay, so now the LCR. So you look at the sharpness and look at the quality factor. Sharpness is given by Q, right? And therefore the omega naught by 2 delta omega, right? So you calculate the omega naught 1 by root LC 2 delta omega. You calculate R by L, and then you divide omega naught L by R. Okay, so you need all three to find out the quality factor. Okay, so note the formulas and make sure you get it right. Now, what is the average power absorbed by a circuit where there is some phi, which is not in resonance, where there is some phi? You have I square R by 2 cos phi, or I square Z by 2 cos phi, right? So cos phi is what? R by Z, right? So I square Z by 2 cos phi, right? Which is the same as V square by 2Z cos phi. Okay? And therefore, you must first find the cos phi, R by Z, right? What is Z? Z is square root of R square plus the A square plus B square, square root of A square plus V square, right? One is the real part is R square, the imaginary part is XL minus XC. XL is omega L, XC is 1 by omega C. Okay? So now you calculate the from that you calculate the Z. Okay, so remember all this. These are all very important results that you must know when you want to understand this material. You must understand the material, but you must also know these formulas: V square by 2Z cos phi. Okay, so when you know all these formulas, life gets a lot easier. Now, so when there is a non-zero phi, you end up with looking at these formulas. Okay, so what is cos phi, what is Z, etc. Once you know all these things, it's very easy to calculate the power. Okay, so power in a capacitive and inductive circuits. So in a capacitive circuit, we already looked at this. A capacitive circuit, 0 to T by 4, power, it is absorbing, then it is discharging, then it is absorbing again. And the inductor is the opposite. It is discharging, then it is absorbing, then it is discharging. Okay, so they are alter egos of each other. Okay, power with both in the capacitor and inductance. So we have both, then one will dominate over the other, and you will have it is net capacitive or net inductive. Okay, so these are all the ideas of true power divided by apparent power is the power factor. True power is VI, or apparent power is VI. True power is what? Power IV cos phi, right? V square by Z cos phi, right? So that is the true power, and then the apparent power is VI, right? And so you divide the two, you have power factor, which is cos phi. Okay, so so That's for as far as LC circuits go. So my suggestion is you take some time and do some problems, download our app, do some problems. Otherwise, just go on the website and do some problems. And when you do problems, only you will know all this material well. And if you do very well, everybody will benefit. In including your family. LC oscillations. So recap of results when resonance occurs when omega equals 1 over square root of LC, right? And you have inductive circuits, net inductive, net capacitive, based on which is bigger, XL is bigger or XC is bigger. Hence we resort to compensation. You can then add another circuit in the side in order to change the effective nature of the circuit. So if it is a very capacitive circuit, you add an inductor in parallel. Okay, if it is a very inductive circuit, add a capacitor in parallel. And using that, you make the circuit more resonate better. So this is very an LC oscillator is like a spring, frictionless spring. Okay, and so what you want is that frictionless spring. That's why you look for resonance. Okay, so LC oscillator is the equivalent of a frictionless spring. All right, so so much for LC oscillators. I think we have dealt with it in great time. You have it in a radio. So if you have a radio, what you do is you adjust the when you turn the radio, you go and adjust either the capacitor or the inductor so that you have resonance at a particular frequency. Then you will hear only that frequency. You want it to be the shape of that quality factor. You want it to be very sharp and at that particular frequency. So when you rotate it, it will adjust the LC resonance. So you'll have one sharp here or there, like that. And so correspondingly you will end up with a different resonance point. Okay, so we also looked at power in an LC circuit, and we looked at power conservation. Now what I suggest is that instead of only relying on what I say, you do some problems and then things will get a lot better. So now I'm going to move on to transformers because we have to make progress. So with respect to the transformer, here is what happens. Okay, so there is an laminated soft iron core. It's not a thick core, but they will have a lot of laminated square with a hole in the middle. This kind of laminated shapes. They will be laminated to avoid eddy currents. Eddy currents will suck up a lot of needless power and heat up the transformer. So as a result, they cut it up into pieces, and you'll have a lot of these square things, and then they will wind it and supply a voltage on this side. When you bind it and supply a voltage on this side, there will be a induced current in the other side. Okay, that's how transformers work. Now, based on the number of coils on this side versus that side, N1 to N2, you will either have a step up or a step down. Which side is bigger, has more coils, that will determine whether it's a step up or a step down. So that is the number of turns in primary. When they say number of turns, they mean how many coils in this side versus that side. And so the flux through each turn of the primary, NP is number of turns the primary. As you know, N d phi by dt will give you Vp, and Vs will be N, also N d phi by dt. Now, when you divide the two equations, you end up with Vs by Vp equals Ns by Np. If Ns, which is S and which is P? This is P, this is S. Primary, secondary. Vs by Vp equals Ns by Np. Right? Vs by Vp equals Ns by Np. Right? So remember that. So Vs by Vp equals Ns by Np. If S is greater then you have a step-up transformer, right? If NS is greater than NP, then your VS will be greater than VP, correspondingly greater than VP, right? Because VS is what? The voltage on this side, on the secondary side, right? So VS is greater than we call it a step-up transformer. What about is doing? You supply a 100 volts AC on this side, you will end up with 200 volts on the other side. If the NS is twice that of NP, if it was 3 times that of NP, you will end up with 300 volts on this side, right? So that is the nature of the step up or step down of the voltages, and this is done using transformers. Okay, and transformers use Faraday's law, right? They induced current on the other side, right? So now, so in an ideal transformer, all the power from this side, which is V times Vp times Ip, will become Vs times Is. All the power will be transmitted. But in a non-ideal transformer, that is not the case. Or as all of you know, nothing is ideal, right? Life, nothing is ideal, you know. So now, if you had, if you had ideal power, you will have Vi equals Vi. Now, so when you load it up like this to 40 volts, 120 to 1, you have R, and you have perfect, everything is perfect, then correspondingly all the power will go to the other side. So I square R, will consume a certain amount of power, and all that power will come from this side, an ideal transformer, right? So this will completely supply, just the only power that will be consumed will be by the resistor, okay? But in a non-ideal transformer, not all power is transmitted, okay? There is a resistance in the windings, and the resistance on the windings is non-zero, okay? So the flux linkage is also not complete. There is a certain self-reactance, and so when you add both of these, you will end up with a ZP, and then you will have a ZS also, so there is an induced EMF across the primary, but it is reduced. Therefore, now VS, but it is also, there is the secondary current will not be VI equals VI, right? So there is some amount of eddy losses in the iron core that also causes, power to go down. So all these three lead to power loss: resistance, eddy currents, and flux linkage. Okay, resistance, eddy current, flux linkage, and there is also hysteresis loss for different reasons. So that's why they laminate. I already explained they will laminate the cores because of eddy currents, right? They will cut it up and they will put, a laminated cores. Now, to take care of hysteresis, they will use soft magnetic material which has low hysteresis. Okay, so remember these two: effect of lamination, and if it reduces eddy currents. For hysteresis, they use a certain different kind of soft core material. Okay, now there is also copper loss which arises due to resistance of the windings. Okay, so that is in the windings that you have, that also is going to cause loss, because that also acts like a resistor. Okay, so there are so many different types of loss, and so correspondingly you can calculate, but I am not going to go into this. So now for a purely resistive circuit, you will have power equals VI, right? Therefore V RMS by R. Okay. So like for a purely capacitive circuit, there is no loss in power, right? And therefore correspondingly the calculation you can a purely inductive circuit, also you know how it works, right? So inductor lags, capacitor leads, etc. Now current lags, right, in the inductor, current leads in the capacitor, right? So so now we have series LCR, and we have looked at this material in great detail over this, right? So this is all the material you'll need for uh, alternating circuits. I've spent a lot of time, 4 or 5 classes with alternating circuits. The reason is that this is one can get a lot of marks here with the alternating circuits if because this is can be understood nicely, and if you read the material carefully, you will get all the value for your studies. So now after this, the next subject we are going to deal with is going to be electromagnetic waves. And so I will briefly introduce electromagnetic waves, because we are also looking at optics in for class 11 right now. And you're of course welcome to attend that, if particularly if you are getting ready for the NEET exam. So now, with respect to electromagnetic waves, let me get started today, but there is no, I'll get started so that, next time we will have introduced the material, So when we look at electromagnetic waves, okay, so um, so I didn't want to go into the displacement current side of detail of things, because we are trying to start a new subject, So basically, after all this was discovered, all these things were discussed, etc., there was this person called Maxwell. Okay, Maxwell, he came and he said there are only 4 things that are happening in electromagnetics. Okay, and he reduced it to 4 equations. Okay, these equations were therefore called the Maxwell's equations. Okay, so 2 of the Maxwell's equations deal with Faraday's law and then Ampere's law. Okay, the other 2 are, one deals with Gauss's law, and the last equation is a very simple equation. It essentially tells you that all magnetism occurs in bipolar ways. That is, there is always a north and a south pole. There can never be a magnet with only a north pole. So you have that. Then you have Gauss's law, which deals with electrostatic charge. Then you had electromagnetic induction, which was Faraday's law, and then there was Ampere's law, which is the current produced. What happens in a current carrying loop, right? So B dot dl equals mu naught I, right? And therefore the Ampere's law was changed little bit to include this idea of this displacement current, which is what we were looking at, right? So they introduced both the conduction current, and then they introduced another term called the displacement current, ID. So I didn't go into the details of this ID displacement current. Displacement current happens in the context of capacitors. Okay, so there is polarization, and polarization also produces current. Although there is no flow of charge, there is no conduction of charge, but then there is this polarization, repeated polarization this way and that way, and also produces what is called a displacement current. So now these are the 4. There are therefore 4 Maxwell's laws. So now for 4 Maxwell's equations. Okay. So the first equation, E dot dA equals Q enclosed by epsilon naught, right? E dot dA over a closed surface, right? That is Gauss's law. B dot dA over a closed surface equals 0, meaning that all magnets only occur in the north and the south pole. Okay. Then the third one is E dot dl equals minus d of B dot dA by dt. Okay. This is Faraday's law. Okay. These are rewritten forms of laws. And finally, this is Ampere's law, where this is B dot dl equals mu naught I, and this is they included this equals mu naught I. This is mu naught I, and then they included this other term, which is the displacement term, mu naught epsilon naught d by dt of E dot dA. Okay, so now these four Maxwell's equations, right, became the basis of all electromagnetic theory. Okay, and so using Maxwell had reduced everything that had been learned, just as Newton had reduced everything in mechanics to three laws plus fourth law, which is gravitation, right? So there were three laws, and then there was gravitation, and therefore that pretty much took care of a lot of mechanics. Like that, Maxwell reduced everything in electromagnetics to four laws. Okay? Now, in free space, the speed of light is also, Maxwell's equation in free space. The speed of light can be derived to be 1 by square root of mu naught epsilon naught, right? C is the speed of light, 3.3 in 10 to the power of 8 meters per second, right? Is equal to 1 by square root of mu naught epsilon naught. Where mu naught is constant you use in magnetism. Epsilon naught is the permittivity of free space which you use in electrostatics, right? So using these two, you can then derive the speed of light. Okay, so now this therefore what Maxwell then said was, he then said that we can explain all these waves, right, like light, and he said light, in fact, of course, if you had when we looked yesterday at diffraction, right, Young's double slit experiment, we discussed this idea that light is a wave. Now what kind of a wave, and what kind of a wave? It is an electromagnetic wave. And how is it able to come across such long distances, right? The sun is so far away, right? And it comes all the way through here, and then it goes in, it comes and hits us, right? Then we have all these waves which deal with, we use the cell phone. It also uses a different type of electromagnetic wave, right? So what are all these electromagnetic waves, right? So these are all forms of waves which which come as a result of an interaction between electricity and magnetism. Okay, and so now when we looked at wave theory in the context of we came up with this two terms, right? One was wave number, 2 pi by lambda, and the other was the angular frequency, which is omega. 2 pi f is omega, right? So we ended up with a sine kx minus omega t, right? And k was 2 pi by lambda, wave number, and the other one was 2 pi f, which is omega, right? So you remember this equation, and I dealt with this in the class 11 material only a few classes ago. Okay, so now using this, one can look at, so at a particular time, right, you have a standing wave, right? So you can look at electromagnetic theory also, by deriving from Maxwell's equations a wave. Okay, so, and that is one of the key ideas. And those waves, right? So what is the velocity of these waves? That velocity is the speed of light, c. Okay, c equals the frequency times the wavelength. Okay, the velocity of the wave is omega by k, if you remember, right? This omega by k will give you the velocity of the wave. Okay, and that same velocity c, this is also velocity of the wave, equals frequency times the wavelength. Very similar. Okay, also waves. Okay, light also is a wave, and it has a corresponding, every wave number gives you the wavelength, and the Omega gives you the frequency, and the ratio of omega and k gives you the velocity of the wave. And this is also frequency times the wavelength. Okay. So now we looked at this transverse and longitudinal waves just recently in the class 11 material. And so we had the stringed instrument, we had the pipe, etc. And then we introduced sound waves where the particles move this way, this way, this way, this way, right? In sound, when I speak like what happens is the particles in front of my mouth, my vocal cords vibrate. When my vocal cords vibrate, right, then I move my mouth like this, like that, right? I produce a pipe, like your tongue, your mouth, all these things, when we speak, right, we produce a pipe, and then there is a vibrator in our vocal cord, and that vibrator vibrates certain way, then the mouth, elongates, and that is how the process of speech happens. Okay. Now, when speech happens, what happens is the sound waves move this way, that way, this way, that way. It produces a vibration in the direction of the flow of the sound. So that's why we call it a longitudinal wave, because the air gets compressed and the energy gets moved this way. In a stringed instrument, however, the stringed instrument, the particles don't move that way. The particles go up and down, right? So that's why it's called a transverse wave. Okay. So now electromagnetic waves are also like stringed instruments. They are not like sound. They are transverse waves, and they can propagate in free space. So the variation of the electrical and the magnetic fields in space produces electromagnetic waves. Okay, the electrical field and the magnetic field are both perpendicular to the direction of propagation of the wave. Okay, if the wave is going this way, the electrical field will be this way, and the magnetic field will be this way. So if the wave is in the z direction, moving the z direction, the electrical field will be in, say, x, the magnetic field will be in, say, y. The cross product of the two, E cross B, is along the direction of the wave. Okay, so this is the basic idea of electromagnetic waves. So here you see, right, the electric field is in this red color. It is in the x direction. The magnetic field is in the y direction, and the wave is propagating in the z direction. So if E, right, E is along the x direction, is I is the vector, unit vector, the x direction, I times E naught sine kz minus omega t, and B is J times B naught times sine kz minus omega t, right? And they have the same, you notice that they have the same k and z, k and omega, right? They have the same k and omega. Therefore, with that, you have the corresponding frequency. Now, the frequency times the wavelength is always c in free space. And what is c? C is the speed of light. Okay, and so this is how electromagnetic waves are propagated. Now, different types of electromagnetic waves will have different frequencies. You all have heard about WIBGR, right? So they will have correspondingly different frequency, correspondingly different wavelength, but they will all have the same velocity. Okay, different frequency, different wavelengths, and different velocity. So see, I've come almost to the end of the material, so I will continue this material again next class, but I would like to request that you take a look at this material, electromagnetic waves, understand this material a little more, understand the speed of light, understand how these things are, and read about it in your textbook. Okay, so if you are going to be taking the NEET exam, you should try to read it in either H.C. Verma, or you should try to read it in the NCERT textbook. NCERT textbook is free. H.C. Verma is 200, 300 rupees. And of course, you can download our app and you can listen to the lectures in addition to my lecture, and also listen to the lectures by the IIT PAL people. Once you do that, you should then attempt some problems. Okay? That is how you keep getting better and better in this material. So that is very, very important for as you go about studying for this exam. So with that, I'm going to stop for today. If you had any questions, let me know. I am happy to answer any questions. Otherwise, we can call it a end of lecture, and we can meet again next week. And I can, for the moment, I want to wish you happy Navaratri, and I will see you again next week. Next Saturday after Vijayadashmi. Otherwise, yeah, okay. Thank you very much. Thank you very much. My best wishes to you, and I hope everything goes well and everything is well for you. My good best wishes. We always want to have all students do well, and so I thank you for attending. But please attend regularly and learn very well. Students who study regularly only, it really helps to study regularly. Please study regularly and attend lectures. But more important that you study all the material very well, and take the exam when it's time to take the exam. All right. Okay. I will see you again next class. Unless you have any questions, we will answer. Okay. Thank you.